So good morning. I'm Krishna Kumar. Welcome to Krishna's class. Last time we were exploring the structure of RNA. We continue with that in this lecture. Now, where we stopped was that you have a collection of k vectors, and then we talk about the span of that. Okay. Now what I want to say is that this what we call the span is the linear combination of these vectors x1, x2, etc. It's something of the form sigma ak ar ai xi I running from 1 to. Now this is the collection that we are talking about. So if I call this S, then this is equal to where AI belongs to R I. This collection, and one can prove that S is space with respect to the usual addition and scalar multiplication in R, which we have already introduced. What you want to prove is that you take, you know that S is a subset of Rn, obviously. Now what you have to prove is that S is closed with respect to addition and scalar multiplication. You know that you take two elements x and y, x of the form sigma ai xi and y is the form b sigma bi xi. Add. You add, you will get sigma ai plus bi xi. That's again of the same form, so it is in S. So for x comma y belonging to S, x plus y belongs to S. This is one part. Second part is for C belonging to R, Cx belongs to S. Cx would be just multiplying these coefficients. That's all. So it's pretty simple. And therefore you see that you have all the ingredients inside S, which will make it a vector space. Okay. Now we extend this notion further. So here we had started with x1, x2, etc. x2. Now we extend this further. So we start with some subset, some non-empty subset of R. So let now here I am going to take a non-empty set. Now what one does is the following. You define A Trigonometric numbers. This is important. Now such collections you get. Now I want to make some remark. Now my claim is that this is quite easy to make. A is a bracket, A is a that again you can prove like this. But what I want to make a remark over this. Sigma summation over I of AI xi is a finite sum. That means you can even use a notation that sigma I running from 1 to infinity or something like that, but with the assumption that AIs would be 0 from some stage onwards. So only a finite number of AIs will be possibly not 0, all others are going to be 0. So that assumption, that way you can use a very nice notation of this kind. But this is make all these connections. Pick a finite number of elements from A and then comment. It's not a fixed element, some finite collection. So all the sums, possible sums of this kind, you take this concept. Okay. So what happens is that in this case the sum will be something like you have two elements x given by a finite sum ai xi and a y, a finite sum bj yj. Both are finite sums. Now what will be the sum of x plus y? X plus y is then a sum of sigma ai xi plus sigma bj yj. Does it make sense? It does make sense because this is in Rn, this is also in Rn, you can add vectors in Rn. So this is well defined, it's a finite sum. Okay. So x plus y belongs to this collection because it is again of the same type. Okay, it is something on the form sigma summation over k ck zk, where it's a finite sum. So that is clear. Similarly for scalar multiplier. So this is very well defined. So you see that every if x y belongs to and so this is clear. So this is a linear space on its own right with the same addition and scalar multiplication that you have in Rn. Or you say this is a vector subspace. So the span of this is called the span of A, Span of A is a subspace of right? But I want to make a comment that the sum that we talk about is only a finite sum. So the remark I wanted to make is the following. It's a finite sum, I have said this. Why is it so? Because if you cannot make any sense out of an infinite sum, because the concept of convergence of sequences will be required to make sense of the infinite sum. You have already seen that on R. See, if you have a series sigma Cn, then how do we give a meaning to it? This is equal to limit n tending to infinity, where Sn equal to the partial sum C. It's a limit of this. So this is the one that is crucial in giving a meaning to it. And this requires a concept of distance on the space. On R we have the usual distance, and in the context of usual distance one can talk about the infinite sum. Up to now I have not introduced a concept of distance on R. I have only introduced an algebraic structure which will involve finite linear combinations, or simply linear combinations, by which you mean only finite sums. So I don't have the instrument to give a meaning for these kind of things. For instance, I cannot talk about sigma xn 1 to infinity each xn belonging to not yet. I don't have a concept of distance introduced in the space, and until I do that, I cannot talk about that. This is always true. That is, whenever you do mathematics, make sure that you talk sense. Because if you want to talk about, suddenly talk about a infinite sum of this kind, then you need suddenly a concept of convergence, which necessarily requires what is called a distance notion, which is at the moment not there. So please bear that in mind. Later we will overcome this if necessary by introducing the concept of distance. That means within the framework of the algebraic structure, you can only talk about finite. So let me just put it in black and white. Within the only finite sums make that's something. So whenever we write sigma ai xi, it means you are always talking about a finite sum. Okay. So linear combination means finite linear combination. So let us drop that word finite for convenience, but always we mean finite linear combination. Okay. So that is to be borne in mind. Now we go ahead further. Make an observation. Talk about the standard basis. I have not said what basis is, but still let me just first part and use the word basis, but later I will make the meaning of this. Okay. Or before that, let me just introduce what a basis is. So we have introduced what is called a spanning set. So there exists a spanning set in R. At least the whole Rn is a spanning set for R. It's not smaller. But with the help of the addition and scalar multiplication, we can reduce this number drastically. And one can easily verify the following. The following set what is a spanning set? We say A is a spanning set provided square bracket A is equal to the whole of R. Okay. So we'll take A to be the collection E1, E2, and where EI equal to delta I1, delta I2, delta IN for I running from 1. So what are the sets, what are the elements of this set? See that the elements of the set are E1 equal to 1, 0, there are n elements. Similarly, E2 will be the second place 0, EI is 0, this is the ith place, 1, or let me write here, I 1, 0. So this is the ith place. And of course EL. Now, first observation is that a span of now this I leave you to verify. Leave it for you to verify. Quite easy to work on that. Take a linear combination which will be an element of R. So A1, A1 plus A2, U2 plus etc. A and En is actually the nth input A1, A2 etc. An which belongs to R. Conversely, you start with any element in Rn, it can be expressed as a linear combination of E1, E2 etc. So that's pretty simple, straightforward. So you see that in Rn, n vectors there exists vectors which span R. So this is something that we observe. Okay. Now you see that if you add to a spanning set some additional vectors, still it spans the whole space. Okay. Suppose you take S, which is a spanning set of Rn, then you put on additional vectors into S, then they also span the whole space. So any superset of a spanning set any superset of that is if A, the span of A is equal to Rn and B contains A, then that's a statement. That's pretty simple to verify. So any superset of a spanning set is a spanning set. That means if this is a spanning set, you add any number of vectors into it, its span is going to be again R. Therefore, you see that if you have a spanning set, you start asking, is it possible for me to draw some of the elements from it so that what you get is still a spanning set? Okay. So the question that you ask is, given a spanning set of Rn, is it possible to find a subset of the spanning set which spans makes a lot of sense, because you see that any superset of a spanning set is a spanning set Therefore, you ask the question, you have got a spanning set already. Can you find a smaller set which spans it? Or in short, what you are going for, asking for is it possible for you to find a optimal spanning set? Optimal spanning set means that a set which spans the space, and possibly if you drop one element from it, then it is no more a spanning set. So you refine the question further. Is it possible for one find a spanning set of Rn whose proper subsets are no more spanning sets. So that's the next question. That is, is it possible to find that? Given spanning set, it is optimal. That's a question there. Is it possible to do that? This is interesting. Can you find a smaller set which spans it? Then that's enough. You don't go for this larger one. Okay? So we'll try to make this spanning set as small as you like. Okay? For instance, you see that if you take E1, E2, etc., En is a spanning set. If you drop one of them, then it is no more a spanning set. What does it mean? This is optimal. Okay? For example, if one drops, remove, or if we take a proper subset of E1, E2, etc., En, it is no more a spanning set. Okay. So one thing that you observe is that if you drop one of the vectors from this collection, it is no more a spanning set. This is a very important observation that we make. Therefore, now we introduce the notion of what is called linear invariance. Make an observation. So you see that consider seen that any vector can be written as a linear combination of E1, E2, etc. Ex. So if you take any x belonging to Rn, x is equal to x1 E1 x1 belonging to R. But if I just take out one element from this, it is no more able to take care of certain vectors. For instance, let us look at R. R3 is with the usual addition and scalar multiplication and put n equal to 3. Now you see that if you take E1, E2, this does not span. What is E1, E2? This is equal to the connection 1, 0, 0 and 0, 1, 0. What about the linear combination of this? C1, E1 plus C2, E2 equal to C1, C2 0. So what happens? You get a reach only up to vectors whose third component is 0. So it's only a part of it. So if the third component is not equal to 0, then you cannot express it in terms of E1 and E2. So also if you drop say E2, if you drop E1, now any proper subset cannot be a something that spans it. But if you have all the three, E1, E2, E3, then it does. Okay. Now what we want to look at is the property of this connection. Okay, identifying such a set. So we want a spanning set which is optimal. Want to identify such sets. So for that we introduced a concept called a linear independence. Okay? Linearly independent means that if you have a set, say it's a linearly independent set, provided one of them cannot be written as a linear combination of the others. Okay? So that's the property. So this is the problem. The problem here is that when you drop E3, E3 cannot be obtained as a linear combination of E1 and E2. Or E2 cannot be written as a linear combination of the rest of what. Okay? So we say that, and this can be reframed to say that, to mean the same thing. We say that a collection of vectors is said to be linearly independent if C1 x1 plus equal to the 0 vector if and only if C1 equal to 0, C2 equal to 0, Ck equal to 0. Okay. Suppose this is not true. What happens? If C1 equal to 0, see this is equal to 0 even when C1 equal to 0, C2 equal to 0, etc. Ck equal to 0 is not true. In that case, what happens? There is some Ca which is not equal to 0. Now I can, in that case, which means xi can be written as minus c1 by ci not equal to 0. Ci minus 1 xi plus 1 minus etc. minus ck by ci x. That means xi can be in that case obtained as a linear combination of x1, x2, etc. xk. I mean with the xi dropped out. Okay. So if this is not true, then this is what you get. Okay. So if none of this can be expressed as a linear combination of the others, then you see that a linear combination of this kind will be 0 if and only if every Ci is equal to Ci. Otherwise, the particular Ci can be, particular Xi can be written as a linear combination of the rest of them. Okay? Therefore, the Xi is redundant in your description because whatever set x1, x2, etc. xk spans, the same set is spanned by x1, x2, etc. xi minus 1, xi plus 1, etc. xk, because that role of xi can be wrong. So you see that this is, I leave it to you to write a proper proof of this. Okay? Take that the definition or realization that a set is linearly independent provided none of the elements in that can be expressed as a linear combination of the rest of them. Take that understanding and then you see that it amounts to this statement. Okay? So what we are looking for is such a set and also such a set that spans the whole space, both these properties together. So you see that the collection En is linearly independent. In fact, that's very quickly one observes this because you see that C1 E1 plus CK EK or CN EN equal to 0 means this is equal to C1 CN. and this is equal to 0 vector implies Ci equal to 0 for I equal to 1. Okay, so that's very quickly verified. In fact, you observe that every proper subset of a linearly independent set is linear. Try to give a proof for it. Suppose you take a set x1, x2, etc., xk which is linearly independent, and then show that you take a proper subset of that, it is also linearly independent. Okay? If not, what happens? If not, you see that there is a linear combination of the one. Suppose you are leaving out x1, x2, etc., xk, and leaving out xi from it. Suppose x1, x2, etc., xi minus 1, xi plus 1, etc., xi is linearly dependent. Okay, so let me use that word. So, definition. If it is not linearly, and this is even only, so there are two things. Given a set, it can be either linearly independent or it can be linearly dependent. Okay, then you say it is linearly dependent. Okay. Now you can easily check this. It is a proper subset of a linearly independent set is not is linearly independent. If not, it is linearly dependent. If it is linearly dependent, then it leads to a coordination. So you work it as an exercise. Okay. Show that. Okay. Show this. Show that. So what you call a basis is an optimal spanning set in the sense that it is also linearly independent. What we call a basis. Subset which is spanning spans Rn and is also a linearly so we have seen the following. Every superset of a spanning set is a spanning set. Every subset of a linearly independent set is linearly independent. Okay? Right? What we are looking for is a spanning set which is also linearly independent, and that you call a basis. Okay? So what you can verify is this E1, E2, En is a Rn has a basis. Okay? Now what one can prove is the following. There are other sets which form a basis for Rn. So the choice of a basis Rn is not unique. That means you have to exhibit another basis. Okay, so let us work with R3. Let us take R3. So for R3, look at this set of vectors 1, 0, 0, 1, 1, 0, 1, 1, 1. What about this set? Does it span? Show that this set is linearly independent and spans R3. Does both. All that you need to do is this. Okay. Take any vector in R. Say A1, A2, or what you want to do is write A1 1 0 0 plus A2 1 1 0 plus A3 equal to if and only A1 equal to 0. This unit, this part. The second part that you have to prove is this. If x1 then your axis it's done. C1 That's quite simple. You have three equations and you can solve them and determine C1, C2, C3 in terms of x1, x2. Okay, so verify these two. That will give you an insight into the working. So what does that indicate? So it shows that given a basis, you can always tamper with it and take out some elements and replace those elements by some other element so that the new set is also a basis. Okay. So there exist several bases for R3. In fact, you can find many more vectors which form a basis. In fact, this is what you can do. Is and only determinant of so this is something. So you have plenty of vectors, collection of vectors which form a basis. So in the moral of the story is that the choice of the basis is not unique. And this is so in general for x1, x2, etc. except. Okay. So the moral of the story is that. Okay. Now let us start working on this idea. So in Rn, what you do is start with A non-zero. Okay. Say x1. Now choose x2 such that x2 is not a scalar multiple of that is possible. Otherwise, x1 itself is a basis for Rn, which is not correct. X1 is a basis for now what you use is look at the span of x1, x2. Now this is properly contained in x3. Okay? This is the span. Since this is properly contained in R, this is the span. Now, show that and show that it doesn't span R unless n equal to 3. Okay. So eventually, suppose you have obtained it this way: x1, x2, xk, which is linearly independent and span of is not equal to, then what happens? You can find an xk plus 1 not in the span of this, but in this. Okay. Then you show that is linearly independent. If it is already equal to Rn, then n equal to k plus 1. Okay? If not, continue. And this cannot continue at infinity. It can continue only kinetically. There's a stage where it will cover the whole of. So starting from a non-zero vector, one can build up a basis for R. Now what we want to assert is the following. That is, every basis exactly n elements. Okay. So what? See, there's a way of proving it in the general scenario, but let me just resort to a mode of proving it in the case of Rn. So we start with the R3. Let us explore. So we prove two things. One, show that every set of n vectors where n is greater than 3 is linearly divisible. This is 1, 2, 3. Set comes vectors. Or more generally, in Rn, so explore the proof of this. Here you can use that E1, E2, E3. Use this. In Rn, you have already a basis, E1, E2, etc. That we already know. In Rn, show that every set of n plus 1 vectors is linearly dependent. So that it's not a linearly independent set. Also, every n minus 1 vectors of Rn does not span so no subset having less than n elements can span the whole space. So it cannot be a basis. No subset having n plus 1 elements cannot be a linearly independent set. Therefore, that also cannot be a basis. Therefore, every basis will consist of only exactly n elements. So the consequence of this is that every basis which are linearly independent and expands the whole space. We have already seen how to construct it. Start with a non-zero vector, keep on constructing it. So you can construct this until you get n elements which form a which spans the whole space. They form a linearly independent set. So you see that, but the important fact is that Rn has several bases, but each one of these bases will have only exactly n elements. Each of them has exactly n . So some of the small things that we did in this process is this. Suppose you start with a linearly independent set in Rn. You can adjoin more vectors to it and make it a basis for Rn. Okay? So there exists given any linearly independent subset of Rn one can adjoin more elements to it. Required to have a basis, consisting of having the given collection as a subset. So this is the one. What it says is that suppose you start with the S contained in R, independent. Then there exists a B such that S is contained in and G is here. And since we have already seen that Rn has, if now Rn has a basis, then it can have only n elements and nothing less, nothing more. Okay? Right? So, because of this system. Okay? So, what one finds is that every basis in Rn has exactly n elements. Although there are several bases, that is possible. And quite often you found that using different bases helps you. Okay? So, depending on the circumstances, you choose a specific basis to suit your description. Okay? So this is possible. So basis is essentially a coordinate system. So in R3 or in R2, let us say, it is easy. So you see that the vector 1 0, the vector 0 1 is a basis. It's a basis. Okay? Now, so also the vector 1 0 with the vector 1 1 is also a basis. What you are doing is, initially when you use 1 0 and 0 1, you are choosing a coordinate system which is a conventional coordinate system. This is your E1, this is your E2. Okay. Now, with E1 you can cover this whole thing. Adjoined to that E2 also, then you can cover not only this but this whole plane, because you see that every vector, if you have any vector here, this can be written as a linear combination of a scalar multiple of E1 and a scalar multiple of E2. For instance, this is E1, C2. Then this is E1, E1. This is C2. But you could also use any two vectors which are linearly independent. In R2, you see that suppose I take R2, so let me draw the conventional to indicate that this is R2. Suppose I choose a vector X. Now what I want is to construct a basis. What I want is, you know that this is linearly independent. X is not equal to 0, therefore this is a linearly independent vector and its span is a line passing through the origin. Now you choose another vector y, where y is not along x. What does it mean? It means that x and y are linearly. Now you can show that together x and y spans the whole space, or this forms a new coordinate system for R. Okay? So any choice of a basis for Rn corresponds to choosing a coordinate system. So you can choose a coordinate system to suit your purpose. Okay? But every coordinate system will consist of exactly n vectors. Now this is what we have proved. In the case of Rn, every choice of coordinate system will consist of exactly n non-zero vectors. Okay? So this is a beautiful result that you have, and therefore every basis will consist of the same number of elements. Therefore, we realize that the number that emerges is an intrinsic number associated with the vector space, and that is what you call the dimension. So this is equal to n. It is exactly the number of elements or this is equal to number of elements in So you say that the dimension of Rn is equal to n because irrespective of the choice of the basis, you see that you have exactly n elements. Okay, so this is what you call the dimension of the vector space R. So R3, any basis you choose will consist of only 3 elements, and you cannot do anything less than that. But if you choose more than 3 elements, then it is going to be, some of them are going to be redundant. Okay? Therefore, every basis will consist of exactly 3 elements. Therefore, we call it 3-dimensional vector space. That's the picture that emerges. Okay? Now let us look at the subspaces of it. Subspaces we have already defined. It is a subset. It is a vector space in its own right with the same sort of operation of addition and scalar multiplication of another space. Okay, now let us see in R3 what are the subspace, or in R2 what are the subspace. You see that the vector 0 is a subspace of R2. Okay. Now you take any line this means you don't have both x1 and x2 simultaneously 0. Okay. So this is a linearly independent set. You take the span of this. Now this is contained in R, which is properly contained in R. And this is a proper subspace, and dimension of the span of x2 is equal to 1. So we take x1 square plus. That means this is a non-zero vector. It's a non-zero vector. Okay. Now you have two vectors chosen which are linearly independent, which form a basis, then you get the whole space. So this means the following. See, this is a vector space. Take a non-zero vector x, then the line Tx is a vector space. Then you take x and y. So you take x not equal to 0, y not equal to 0, x comma y linearly independent. Then it is a whole space. So what are the subspaces of R2? Subspaces of R2 are one, 0, 2, all lines passing through the orbit. Each one is a one-dimensional vector space. 3. Okay. So any line passing through the origin is generated by a non-zero vector, which is linearly independent, a single vector. So it is a basis for that. So that subspace has dimension 1. So you have a 0-dimensional subspace, a 1-dimensional subspace, and a 2-dimensional subspace. Both 0-dimensional and 2-dimensional are trivial subspaces. A proper subspace that you have consists of all lines passing through the origin. Okay. What about R3? R3 has again 0 which consists of the zero-dimensional subspace. Then all lines passing through the origin, which is generated by non-zero vectors. Then all planes passing through the origin, which is generated by linearly independent pair of vectors in R3, which consists of all planes passing through the origin, and then the whole space, which is generated by 3 linearly independent vectors. Okay, so you have subspaces of dimension 0, dimension 1, dimension 2, dimension 3. So dimension 1 subspaces are lines passing through the origin. Dimension 2 subspaces are planes passing through the origin. Dimension 3 subspace is the trivial one, namely R3 itself. Now, pushing this idea forward, you see that Rn has n plus 1 different types of subspaces. What are the subspaces? It is the subspace generated by the zero vector, which is a zero-dimensional vector space. Subspace generated by a single non-zero vector, which is essentially a line passing through the origin, and two-dimensional subspaces, which is generated by a pair of linearly independent vectors in Rn, and so on. If you take k linearly independent vectors in Rn, then the subset or the subspace spanned by them forms a subspace of Rn whose dimension is equal to k. So you can get subspaces of dimension 0, subspaces of dimension 1, subspaces of dimension 2, etc., subspaces of dimension n, which is the whole space. Okay, right? So this gives the scenario of all subspaces of Rn. Now we will explore this Rn further in the next lecture. Thank you very much.